Good. So it is my pleasure to introduce Pierre-Henri Chaudouard from Paris and his talk on recent progress on the Gan-Gross-Prasad conjecture for unitary groups.
Thank you. First, I would like to thank the organizers for the invitation. It's a pleasure to speak at your seminar. So my talk will be based on first joint work with Raphaël Beuzart-Plessis and Michal Zydor, which is available on the archive, and second on the ongoing joint work with Raphaël Beuzart-Plessis. I've changed my slide, it's okay?
Yes.
Okay. Thank you. So first, let me begin with some notation. So I will consider quadratic extension E over F of a number phi. I will denote C the non-trivial element in the Galois group of E over F, and we'll fix n an integer, and curly Hn will be the set of isomorphism classes of non-degenerate C Hermitian spaces H over E of rank n. So let me pick a Hermitian space of rank n. So to such an H, I define some unitary groups. So the first one, which is denoted by UH prime, is the automorphism group of H. And the second one is in fact a product of a unitary group, the product of UH and the automorphism groups of the Hermitian space of rank n+1 obtained by taking the orthogonal sum of H and the one-dimensional Hermitian space given by the norm of E over F. And moreover, the group UH prime is viewed as a subgroup of UH via the embedding given matricially like this. I will denote A the ring of adels of F, and between two bars the product of the normalized local absolute values on the completions of F, the local completions of F. I will denote P a parabolic subgroup of UH, which I recall is a product of unitary groups, and I will pick Levy decomposition Mn of P, with M is a Levy factor and N is a unipotent radical of P. And I will consider the space of cuspidal automorphic functions on M. So I assume that the function I consider are left invariant by some canonical central subgroup, which is isomorphic to some copies of the neutral component of the multiplicative group of R. And by cuspidal automorphic representation of M, so I will denote it by sigma, I mean an irreducible factor of the space of cuspidal automorphic functions. So to such objects, I will attach Eisenstein series in the usual fashion. So this is just a matter of notation here. So first I introduce the group of algebraic characters of P defined over F. And by tensoring it with R, I get the group of real unramified characters of P of A, so the adelic points of P, and also we get the complex unramified characters of P of A. I will denote AP, the dual space of AP star. So we have a canonical morphism from P of A to AP. So because I can take the pairing, the canonical pairing between a character chi and P an element of P of A, I can take the normalized absolute value and take the logarithm in such a way. I have a morphism from PA to AP, and I can extend this morphism to a map denoted by H sub P to the adelic points of the product of unitary group UH to AP, simply by using the Iwasawa decomposition. So any element of UHA can be written as a product of an element of P of A and an element of K, where K is a good maximal compact subgroup that I fixed inside the UH of A. So remember that sigma is the cuspidal automorphic representation of some Levy factor of P, and I can induce this. I can take the smooth induction of this representation, and in this way I get the space AP sigma of UH. So this is it can be described as a space of automorphic function that satisfies some condition. The restriction to M is essentially belongs essentially to sigma. So then I can take a complex anonymized characters of P and phi, an automorphic function in this space AP sigma, and I can form the usual sums that gives the Eisenstein series. So of course it is as usual convergent in some region, and in general we take an analytic the analytic continuation to all AP C star. So I will denote my Eisenstein series EX phi lambda. So now I introduce the Ichino-Yamana regularized periods. So what I want to do is to integrate. So the Eisenstein series is a function on UH of A, and I want to integrate it over the diagonal subgroup UH A prime. In fact, the quotient of UH A prime A by the group of rational points. So in general, this integral is not convergent because the Eisenstein series is slowly increasing but not rapidly decreasing. So of course, it may be convergent. For example, if I take P, the group UH itself, then I integrate a cuspidal function which is rapidly decreasing. So this is a case where the space AP is reduced to 0. So I can integrate because it is rapidly decreasing. But there are other non-trivial, non-trivial Eisenstein series we can consider. This is the case where P is the product of U of H on one side, and on the other side P prime, where P prime is a maximal parabolic. Then once again, the Eisenstein series we get, so it is a real Eisenstein series on one factor, but a cuspidal function on the other factor, and then it is also rapidly decreasing, so we can integrate. But in general, it has to be defined by some truncation procedure introduced by Ichino and Yamana. So they define a truncation operator. You can apply it to the Eisenstein series, and then you get a rapidly decreasing function on UH prime, and then you can integrate it. And so the truncation operator here depends on the parameter t, but we can, if we follow Ichino and Yamana, one can analyze the behavior in t of this convergent integral. It is a polynomial exponential, and you can take the constant term, and for almost all lambda, say, we obtain the regularized period, and if the integral is convergent, then we we get the same result. So it is compatible with the usual integral. And so the regularized period, so it has so we view it as an analytic function in lambda. It may have poles coming from the Eisenstein series, and also poles coming from the procedure of defining regularized period. But in the cases we shall consider only the pole of Eisenstein series can happen. Okay. So we have this period of Eisenstein series, and I can state two problems. The first one, I call it the Gan-Gross-Prasad problem, GGP problem, is to find a condition for which there exists a Hermitian form H, parabolic subgroup P, and the cuspidal representation sigma of some Levy factors of P, unitary unramified character lambda in I AP star, so I is the square root of -1, such that the linear form defined by so the regularized integration over UH primes of the Eisenstein series associated to phi and lambda does not vanish identically on the induced space of sigma. And there is also the problem of the refinement of this problem. This is, I call it the Ichino-Ikeda problem. The problem is to express the squared modulus of the period in terms of natural local analogues. So we will see solutions for this problem for representation sigma that satisfies some specific condition defined in terms of base change to linear groups. So of course, if P the parabolic subgroup of UH is a UH itself, this is the original Gan-Gross-Prasad conjecture about a unitary group, and the original Ichino-Ikeda conjecture about the squared modulus of periods. So to explain the condition and the representation I consider, I have to introduce what I call a regular Hermitian Arthur parameter. So I consider the group GLN-E. So as a group over F by restriction of scalar from E to F. So I denote the F group that I obtain by Gn, and I consider G the product of Gn by Gn+1. If I take a parabolic subgroup Q of one of these two factors, and pi a cuspidal automorphic representation of Levy factor MQ of this parabolic Q, so I can decompose the Levy as a product of a linear group of the same type as a Gn. So I will write here this decomposition, and accordingly I can decompose the cuspidal representation pi as a tensor product of a cuspidal representation of each factor. So of course I can do the same for each factor, and I put an index k to denote what is relevant to the factor k for k is n or n+1. So I take a cuspidal representation pi n for the Levy MQn of Qn, and in the same way a cuspidal representation pi n+1 of the Levy M NQ n+1, and I can induce this the tensor product of this representation from Qn cross Qn plus 1 to Gn cross Gn plus 1. And in this way, I get a representation of G of L that I denote by capital Pi. So I will say that capital Pi is a regular Hermitian Arthur parameter. So if for each factor, the component, so first condition, the component I get for each factor, so let me fix K, the component for the factor indexed by K are 2 by 2 distinct. First condition. The second condition is that if the factor is a self-conjugate dual, so I write it pi I is equal to pi I star, a star. So in this case, we know that so the ranking, the Selberg function attached to pi times the conjugate of pi, then is supposed to have a pole at s equal 1, and this L function factorizes as a product of two SI L function with a sign plus and minus 1. So the condition we assume is that pi I has the right sign according to K. That is, if K is odd, then this is SI the plus SI L function of pi I that has a pole at s equal 1. And if K is even, then it is the contrary. So we have this well-known SI L function dichotomy. This is related to the distinction that is to the period, the twisted periods according to the subgroup GLN F for each factor. So this is well known. And the third condition is that if a component for K is not self-conjugate dual, then its conjugate dual has to be a factor itself for the same K. And the fourth condition, so which is in some sense a convenient condition, which is outside the point of view of Arthur parameter, is that if pi I is a component on the n side, so for Gn, then its contract gradient is not a component in the Gn plus 1 side. So this is this fourth condition is really a convenient condition for us. This is some kind of artificial condition. So if so we have the special case of discrete Arthur parameter. So this is a case where all the components pi I n and pi I n plus 1 are self-conjugate dual. And we have the condition 1 and the condition 2. So in this case, if all the representations are self-conjugate duals, then the condition 3 is empty. So because they are self-conjugate dual. And so what I want to emphasize is that in this case, the fourth condition is automatic because of the dichotomy of the SI L functions. So the fourth condition is automatic. So if you are just interested in the original GGP conjecture, so you can forget condition 3 and condition 4 and assume that the representation pi I are all self-conjugate dual. So we have this this representation pi n with this decomposition. I take the tensor product. I denote this representation pi. and capital pi is the induced representation. So I fix such representation capital pi. So with the previous condition, so this is in my sense a regular Hermitian Arthur parameter. So I attach to pi a permutation W, which exchange the factor GNI and GNG for some k is 1 or n plus 1, if the representation attached to the factor GNJ is a conjugate dual of the representation attached to the factor GNI. So in this way, I can define a subspace of unramified characters of the parabolic Q of G, which is the subspace of unramified character that are anti-invariant under W. So this will be our space of parameter and for our space of unramified characters. And for such unramified characters, I can twist my representation small pi by lambda and induced to G. And in this way, I get capital pi sub lambda, so the twisted version of pi. Is it okay for everybody? Is it okay?
Yes,
yes?
It's okay. It's okay.
Okay, thank you. Okay, I am a little alone in front of my screen. Thank you. Okay, so now let sigma be a cuspidal representation of the Levy factor of some parabolic subgroup P of UH. So this is the unitary case, the product of unitary groups here. And we say that capital pi is a weak base change of the induced representation from sigma to UH if for almost all places V of F split in the quadratic extension E, the local component pi V of pi is the split base change of the local component of the induced representation. Okay, so it is a convenient definition, easy to state. And if it exists, the weak base change is in fact unique by a result of Ramakrishnan. And moreover, in this case, we can identify by some base change isomorphism the space of non-unified character of P and the subspace I have the subspace of unramified characters of Q, so denoted by AQ pi, attached to the parameter pi. So I can now state a theorem about the Gan-Gross-Prasad problem. So let me fix capital pi a regular Hermitian Arthur parameter and lambda some unitary unramified character in my subspace AQ pi. Then the following two assertions are equivalent. First, the Rankin-Selberg function attached to pi sub lambda is non-zero at 1/2. And the second assertion is that there exists a Hermitian form H, a parabolic subgroup P of UH, and the cuspidal representation sigma of the Levy factor of a Levy factor MP of P, such that the weak base change of the induced representation from sigma is capital pi, And moreover, the linear form, so defined by the period of the Eisenstein series attached to phi, where phi is a vector, is a function in the induced representation from sigma, and the character lambda, which is attached to the character BC of lambda. So this is a character of P attached by my base change to lambda. So if this linear form, so I recall that this period is essentially the integration over the subgroup UH prime, the quotient by rational points, in fact, of this subgroup, suitably regularized. So if this linear form does not vanish. So of course, this theorem is an extension of a theorem due to several authors, as I will recall. I want to mention that under our assumption of pi, in particular, our regularity assumption on our parameter, the map lambda, the map which associates to lambda the period of the regularized period of the Eisenstein series is in fact holomorphic on the space IAQ pi. So we first, of course, the Eisenstein series is holomorphic on this space of unitary unmodified characters, but even the regularized period is also holomorphic in this case. And third remark, we can state stronger versions of this theorem by requiring some uniqueness in the assertion 2, but I will not discuss this problem here. It relies on the so-called local Gan-Gross-Prasad conjecture. Okay, is there any questions so far? Okay. Okay, so let me remind you some previous works. So they concern the case of the original GGPconjecture. So this is a case of the parabolic P of UH is UH itself, and then the implication 2 implies 1 has been obtained, so in part in the work of Ginsburg, Jacquet-Rallis, or Ichino Yamana, and fully in the work of Diwa, Zhang, and Lei-Zhang, by different methods than we use here. So here the proof follows the Jacquet-Rallis strategy. So it is based on the comparison of relative trace formulae. And of course, important works in this similar vein have proven this theorem under different hypotheses. So first, we have a series of results when there is so when we assume that pi is cuspidal, and moreover that pi, so the parameter pi has to be cuspidal, and moreover it has to satisfy some local hypothesis. So I can mention the work of Wei Zhang, the work of Han Chui, who considers the problem of the Archimedean transfer, and the work of Beuzart-Plessis. And then there was a work of Beuzart-Plessis, Liu, Zhang, and Chu, who proved the theorem in the case of a general cuspidal pi. So general Hermitian Arthur parameter, which is supposed to be cuspidal, but with no local hypothesis. So in our work with Beuzart-Plessis and Zydor, we get also the case of non-cuspidal pi, so the so-called endoscopic cases of the Gan-Gross-Prasad conjecture for unitary groups UN cross UN plus 1. Okay, so let me now consider the refinement of the statement. So the refinement à la Ishino Ikeda. So we fix Hermitian space H, a pair P sigma as before. So P is a parabolic subgroup of our product of unitary group, and sigma is a cuspidal representation of a Lady factor of P. And we assume that the weak base change of the induced presentation is a regular Hermitian Arthur parameter, so denoted by capital pi. We shall identify in the following the space of character of P and my subspace AQ pi. So in this way, for any character of pi, I can define capital sigma sub lambda, the induced representation obtained by tensoring sigma by lambda, and in this way I can also, because I identify these two spaces, I can tensorize pi by lambda also and induce to G. So in this way I get pi sub lambda. I introduce another hypothesis. I assume that all the local component sigma v of sigma attached to any place v of f. So we assume that the local component sigma v are tempered. And we will use the Tamagawa measure on UH and the UH prime, the adelic point of this group. And we fix a factorization of such a measure, and we assume that for almost all places V, the volume of the maximal compact subgroup given by the OV point, where OV is a ring of integer of FV, is of volume 1. So thanks to this local object, I can introduce the local periods. So I decompose the representation pi lambda into local components, the representation sigma lambda, and I consider also the quadratic character attached to E over F, and I decompose it into local characters. And we define a ratio of local L-function. So first we have a product of abelian L-function attached to the power of the quadratic character eta v. And we have a ratio of, so on the numerator, we have a local ranking Selberg factor attached to pi lambda. And on the numerator, I have a so-called adjoint L function attached to a sigma lambda. So in fact, sigma lambda is a tensor product of two representations for each factor of the product of unitary groups. And here we can this is a shortcut for the product of the adjoint function attached to each factor. So this can be defined in another way. If you prefer, you can define this factor as an L function attached to pi lambda v. Then I fix an invariant inner product on the induced presentation sigma v, and taking an element hv in the subgroup UH prime. So I can consider the action of hv on a vector, a non-zero vector in sigma v. So I have sigma hv phi v. I take the pairing with phi v, and I integrate this pairing again against the measured hv along the subgroup UH prime, the heavy points of UH prime. So for lambda unitary, this integral is convergent, and moreover, the local factor has neither pole nor zero at 1/2, and I can normalize this integral by dividing by the L factor at 1/2 times the pairing of phi v with itself. And in this way, I get an analog of the period, a local analog of the period, which is normalized in the sense that for almost v and non-zero and -5 vectors, phi v, the period is 1 on such things. Okay, so now we have the second theorem, which is an extension of the Ichino-Ikeda conjecture. So I take phi, a vector in my induced presentation, which I suppose to be non-zero and decomposable. So phi v as a local component. Then I can write the squared modulus of the regularized period of the Eisenstein series, divided by the squared of the norm, the Peterson norm of phi, as a product of some constant, and the product of all the local periods. And the product is in fact finite here. So what is this coefficient? So first, S pi is a two group attached to the Hausser parameter pi. And this is the order of the group. And we introduce the global L function, so defined in some region by the product of the local L function attached to the induced presentation sigma sub lambda. And we take essentially the value at 1/2, but we have to regularize it in some way, because in this situation, the adjoint L function may have a pole, and so we have, so this is the denominator. The denominator may have some pole, so we have trivial zero for this global L function. In fact, a ratio of L function. So I put this factor here, and I take the value at 1/2 of this product. So this is this constant. So for P, if the parabolic subgroup P is equal to the unitary group UH, this is in fact the Ichino-Ikeda conjecture for unitary groups, and it has been proven by first Wake-Jung, and then Beuzart-Plessis. So for Arthur parameter pi, which is assumed to be cuspidal, and which is assumed to satisfy some local hypothesis. But in the work of Beuzart-Plessis, Liu, Zhang, and Zhu, the local hypothesis had been removed. According to them, the Ichino-conjecture, the Ichino-Ikeda conjecture for unitary groups holds in general for pi cuspidal. And in our work with Beuzart-Plessis and Zydor, we extend the work of Beuzart-Plessis, Liu, Zhang, and Zhu to the case of non-cuspidal pi. And here the statement is more general because we are considering Eisenstein series. So, is there any question? Okay. So now I want to discuss some application to this to theorem 1. So the GGP conjecture for periods of Eisenstein series. So this is the application is about Bessel periods. So we fix two integers n and r. So H is as before Hermitian space of a rank n, and H prime is a specific Hermitian space of rank 2 r plus 1. So this is a sum of two maximal isotropic subspaces in duality plus non-isotropic vector plus a line generated by a non-isotropic vector. So this gives a quasi-split. So the automorphism group is a quasi-split unitary groups of odd rank. So I fix some bases in duality for each maximal isotropic subspace I have fixed, and attached to such a basis, I can attach a flag of isotropic subspaces in this way, and I get a parabolic subgroup which stabilizes this flag, the parabolic subgroup, which is a subgroup of the automorphism group of the Hermitian form obtained by considering the orthogonal sum of H and my form H prime. So as before, UH prime is an automorphism group of H, but now my bigger group, my product UH is a product of UH times a unitary group attached to H plus H prime. And as before, we have diagonal embedding of UH prime inside UH. Let NB be the unipotential radical of B. Then the group UH prime normalizes the product of the trivial group and the unipotential radical of B. So we can consider the semi-direct product of this group by UH prime, and in this way we get a subgroup of UH, and this is the Bessel subgroup. So to define Bessel periods, I need some additional data. I fix an additive character of the ADEL of E, trivial on E, and I can define by this formula the character of NB of A, which is invariant under conjugation by UH prime. And in this way, we can extend, so I denote my character always by psi, So I get a character of the identity point of the Bessel subgroup, which is trivial on UH prime. Let me pick a cuspidal representation of UH, and then the Bessel period is obtained by integrating an automorphic function in the space of sigma against the character psi along the quotient of the identity points of the Bessel subgroup by its subgroup of rational points. So let me recall that if n is 0, then the subgroup UH prime is trivial in this case, but UH is then a quasi-split unitary group of odd rank, and then the Bessel subgroup is the maximal unipotent subgroup of UH, and the Bessel period is in fact a Fourier-Whittaker coefficient of phi. So now let me state the Gan-Gross-Prasad problem for Bessel periods. I find a condition for which there exists H and sigma so that the Bessel period BH does not vanish identically on sigma. Of course, this is given by the GGP conjecture. So to state the theorem, I have to put a condition on sigma that is stated in terms of Arthur parameter. So I will. So this is essentially as before. So simply I have to replace the group Gn plus 1 by the group Gn plus 2R plus 1. And the definition of the discrete Hermitian Arthur parameter, so is as you guess and as you know, this is an induced representation from a parabolic subgroup of G, and I require that the representation I start from has a decomposition on each factor. So the components are 2 by 2 distinct, and each representation is self-conjugate dual with the right sign. So this condition is expressed in terms of the RHAP function. So this is I think a classical definition. And the theorem is as follows. So let pi be a discrete Hermitian Arthur parameter. Then the following assertions are equivalent. The Rankin-Selberg function attached to pi at 1/2 is non-zero. First assertion. And second assertion, there exists a Hermitian form H, a cuspidal representation sigma of UH, so that the weak base change to G is pi. So the weak base change. So this is as I defined it in the previous slide. So there exists a Hermitian form, a cuspidal representation sigma of UH, so that the weak base change of sigma to G is pi, and the Bessel periods does not vanish identically on the space of sigma. So if n is 0, so we saw that the Bessel period is a Fourier-Whittaker coefficient, and then the group UH is a quasi-split unitary group, and then so the theorem in fact is proved by Ginsburg-Rallis and Chaudouard by the method of descent. That the assertion 2 implies assertion 1 is proved by Dewey, Jiang, and Lei-Zhang by a different method than ours. So in our approach, the theorem 3 is in fact deduced from theorem 1 for some Eisenstein series associated to a maximal parabolic subgroup of a product of unitary group UN cross UN plus 1. And also, we in this situation, we expect to get the refinement a la Ichino Ikeda as conjecture by If and Liu. But okay, so we have to write the details. So, okay, so in the following minutes, I want to give some ingredients in our proof, and which progress on the trace formula enabled us to get this theorem. So this is about. So now I will just speak about theorem 1 in the case of the original Gan-Gross-Prasad conjecture. So the period of cuspidal automorphic forms on the product of UN plus 1. So we go back to the notation at the beginning of the talk. So UH is the product of UH times U of H plus say the norm. So as I said, we use the Jacquet-Rallis relative trace formula. So first, for the double quotient of UH by so on the right and on the left by the subgroup UH prime. So the principle is to integrate the automorphic kernel obtained by the sum of rational point of UH of f x minus 1 gamma y for some test function f on UH of A. So we integrate this automorphic kernel so in each variable over the subgroup UH prime. And the principle is to have a geometric decomposition and a spectral decomposition. So here we focus on the spectral decomposition. So of course, I have to say that the integration is in general not convergent. So we have to introduce a truncation process, but Zydor has done this, and he was able to make sense to this integral, and he got a spectral expansion, coarse spectral expansion of this expression, according a cuspidal data of UH. So if chi is a cuspidal data given by the class of a pair UH sigma, where sigma is an automorphic representation of UH, then the spectral contribution in the trace formula is given by a relative character, which is built upon periods given by integration, so the period pH, which are given by integration along the subgroup UH prime. So this is the simple case of my periods of Eisenstein series. And in fact, we sum over an orthonormal basis of the periods of phi where f act times the conjugate of the period of phi. And we compare this relative trace formula to some other Jacquet-Rallis trace formula for linear groups. So we go back to our linear groups G, which is a product of gln E times gln plus 1 E. And we distinguish two subgroups inside G, which is first we have the group gln, which is diagonally embedded in G, and second we have the group G prime, which is a product of gln F times gln plus 1 F, which is naturally embedded inside G. So we can consider the relative trace formula for the quotient G mod H mod G prime. So here we consider the automorphic kernel attached to a test function on GA. But this time we integrate the first variable on the group H, and the second variable we integrate over the group G prime against some character attached to the quadratic character relative to the quadratic extension E over F. So the second integration is to take into account the ASI dichotomy, the dichotomy between distinction and SI distinction. And the first variable is the Rankin-Selberg integration. This is reminiscent, of course, to the Rankin-Selberg construction of L function. So I put quotation marks. Of course, this integration does not make sense in general, but there is a truncation process given by Zydor, and Zydor got also a spectral expansion of this distribution according to cuspidal data of G. And one of the key ingredients of the case of non-cuspidal pi for the GGP conjecture is the following expression for the cuspidal, the spectral contribution attached to a cuspidal datum given by a pair Q pi, such that the induced presentation is a discrete Hermitian Arthur parameter. So in this case, the spectral contribution is given up to a power of 2 by a relative character, which is defined as follows. So the relative character is obtained as before by a sum over some orthonormal basis of the space AQ pi of two ingredients, the product of two ingredients. First, the Rankin-Selberg period of the Eisenstein series E phi, so associated to phi, and the parameters the 0, that is the trivial ununified character. So here this is so of course this is given by a priori an integration of an Eisenstein series along the subgroup H, but it is not convergent. So we take the regularized Rankin-Selberg period as defined in the work of Ichino and Yamada. And the second period which appears, in fact, so we take the complex conjugate of it, is in fact a simple case of an intertwining period, in the case of Flicker-Rallis periods, which was introduced by Jacquet, Lapide, and Rogasky. And the main point in this relative character is that we can deduce from the work of Ichino and Yamana that the distribution I pi does not vanish if and only if the central value of the Rankin-Selberg attached to pi does not vanish. And now our first theorem in the original GGP setting is a consequence of the following theorem. So that we obtain with Beuzart-Plessis and Zydor, is that if pi is a discrete Hermitian Arthur parameter, and if we have test function f, and for any Hermitian space of rank n function fh with matching local orbital integrals. So this is a local condition I don't want to state here. Then the relative character attached to pi up to power of 2, an explicit power of 2, is in fact the sum over all Hermitian spaces, over all cuspidal data UH sigma, such that the weak base change of sigma is capital pi, of the relative character attached to the group UH. The representation chi or sigma, if you prefer, if sigma is represented by UH sigma, and the test function fh. So in this case, it is not difficult to deduce the theorem 1 from such an identity. And to finish, I want to mention some important ingredients we need to obtain this identity. So first, so the last theorem is based on the existence of enough test function with matching local orbital integrals. So this means that we have the non-Archimedean transfer due to Wei-Jiang. We have also the fundamental lemma in this situation, which was stated by Jacquet-Rallis and proved by Yoon and Gordon, and then reproved by Beuzart-Plessis. And unfortunately, we do not have completely the Archimedean transfer, but fortunately, thanks to Ang Shui, we have a partial result towards the Archimedean transfer, which is sufficient for the moment for applications. And moreover, we have a full comparison of the Jacquet-Rallis trace formula. This is due to Zydor and myself. So for test functions with matching local orbital integrals, we have an identity between the relative trace formula for the group G and the sum over all Hermitian spaces of rank n of the relative trace formula for the group UH. And the problem is from this identity, so each distribution has a spectral expansion, but we want to isolate some identity inside this sum. And for this, we use the method of isolation of cuspidal datum, which appears in the work of Beuzart-Plessis, Liu, Zhang, and Shu. And to make this method work, we have also to use an important ingredient, that is the spectral characterization of transfer due to Beuzart-Plessis. Okay, so thank you. I will stop here.
Thank you very much. Questions, please.
Yes. So I would like to ask a question regarding the even orthogonal case. If you have some works or thoughts on the analog for even orthogonal groups.
Yeah. You mean? What do you mean? UN cross UN or?
The identity. Maybe you can go a few slides back.
Yes.
So the Gan-Gross-Prasad conjecture for the even orthogonal case. You had some formula, maybe.
No. This is here we are in the even corank case.
Yes, but that's for
I don't say anything about the even corank. If this is your question.
Yes. So this was of course for the unitary case, and I was asking if you have some thoughts on the even orthogonal case.
You mean GGP for orthogonal groups? Well, no. so probably at last there is a student of Wei-Jung who worked on this question. So perhaps he has an approach through some relative trace formula too. Okay, if I have to speak about the trace formula method, personally I have nothing to say about orthogonal group, but at least there is a student of Wei-Jung who is working on it.
Further questions, please?
How about the rank, not a UN n-1 case, like a general pairing?
Okay, so Anju has some works about relative trace formula in the UN cross UN case. So maybe you can imagine that you can make progress in this situation too. But probably you have to reduce some works we have done in the UN cross UN plus one case.
Okay, any further questions? If not, let us thank the speaker again.
Very good. Thank you.
Thank you.
Next week, we will have a talk by Tian Fan Yang on a related topic. Wait a second, let me tell you which one. It's period relations on standard L-functions of symplectic type. A little bit raised. So see you all next week. And thank you very much again for your wonderful talk, Pierre-Henri.
Thank you. Thank you very much for the invitation. It was my first time on such a seminar. Good experience.
Merci bien.
You're welcome to visit here in person when it becomes possible.
Thank you. Okay, what I am supposed to do? I can stop the.
I think I will now close.